So in this discussion, you are going to see how different organs, such as liver, muscle, adipose tissue, and brain, how they will coordinate in metabolizing food of different types, carbohydrates, lipids, proteins, etc., and how they coordinate with each other in order to sustain energy in every cell in the body under different conditions, under well-fed state and under a fasting or starvation state. So we are going to see how each of these organs metabolizing these molecules, carbohydrates or others, and how they sustain energy with each other to other organs. ليش هذا مش راضي يجي كده؟ So these are the organs that I am talking about: liver, adipose tissue, brain, and muscle. Now the metabolism and the coordination between these organs is controlled and regulated by hormones. Okay? And here mainly I am talking about insulin and glucagon and some other counter-regulatory hormones of insulin such as epinephrine, cortisol, or growth hormone. So hormones and availability of the substrates, carbohydrates or lipids or proteins, will regulate how these organs will metabolize things and how they will be coordinated with each other. Okay? Okay. These are some concepts you have to remember when we discuss integrated metabolism. Some of these concepts is that major tissues such as liver, adipose tissue, muscle, brain work together in order to maintain a constant supply of oxidizable fuels. What are the oxidizable fuels that we are talking about? Glucose, ketone bodies, fatty acids. So we are going to see how these oxidizable fuels are supplied by different organs and how they will collaborate with each other. In the liver, in the well-fed state, the liver is considered as glycogenic organ. In well-fed state, liver is glycogenic. What do we mean by glycogenic? يعني synthesis of glycogen. And we are going to see why in well-fed state liver is glycogenic, why it is glycolytic, why it is lipogenic, and why it is cholesterologenic. Okay? The major reason is the high insulin to glucagon ratio. How this ratio make liver in the well-fed state having these characteristics, we are going to look at them in some little details. The liver also in the fasting state is considered as glycogenolytic organ. ايش يعني glycogenolytic؟ يعني degradation of glycogen. Glycogenolysis. And the liver is gluconeogenic. Okay? يعني synthesizing glucose from non-carbohydrate substrates like some amino acids, lactate, glycerol, etc. And the liver also in the fasting state is considered as ketogenic. Ketogenic يعني synthesizing ketone bodies. An example of ketone bodies, the acetoacetate and beta hydroxybutyrate. You are going to see how liver and why liver synthesizing ketone bodies in the fasted state, and how the liver did not use them as a source of energy but sent them to brain, okay, at that condition, because as you know, brain mainly relies on glucose, but under some conditions like fasting, brain will adapt itself, not only relying on glucose, it will decrease its dependence on glucose as a source of energy and looks for a new source such as ketone bodies. Ketone bodies, brain cannot do ketone bodies. They are synthesized in the liver and sent to brain to be used. So the proteolytic also, يعني some amino acids, okay, some proteins will be degraded into amino acids, okay, for gluconeogenesis purposes. The strategy of metabolism is to store the sources of fuels when food is available and mobilize these when food is not available, or when these supplies are or store energy sources are needed. Okay, and this is what we see in high insulin glucagon ratio, and this is what we see when glucagon to insulin ratio is high. Okay, so this is represent the catabolic picture, and this represent the anabolic picture of metabolism. This is the insulin that I am talking about. Insulin is a peptide hormone. It is synthesized as a pre-pro hormone or pre-pro protein. Then it will be processed and converted to insulin molecule. This is the active form of insulin. The pre-pro or the pro-insulin are not active forms, okay? And these non-active forms will be activated by proteolytic cleavage of some peptide found here, okay? And that peptide is called the C peptide, or the connecting peptide that connects this portion of insulin with this portion of insulin. Very good. Insulin is considered as anabolic hormone. And what do we mean by anabolic hormone? يعني for synthesis. Okay, it will stimulate synthesis of glycogen. It will stimulate synthesis of proteins. It will stimulate synthesis of lipids for storage to be used when needed in the cell. Glucagon is catabolic. Catabolic يعني بيعمل degradation لا هاي المواد، بيعمل degradation للكربوهيدرات، okay, بيحول الجلايكوجين إلى جلوكوز، بيعمل degradation of proteins، بيعمل proteolysis، بيحولها إلى أمينو أسيدز، بيعمل degradation للليبيدز، يعني بيعمل لايبوليسيس، بيحولها لترايجليسرايد. أوكي؟ وبيحول الترايجليسرايد لجليسرول وفاتي أسيدز. إنه أنابوليك بتنفصل عنهم. هاي في هون polypeptide تمتد like this and connecting here. This is called the C peptide or the connected peptide. Upon proteolytic cleavage here and here, it will be released out and we will remain with this molecule of insulin, which is the active one. These are the stimulants for insulin secretion: glucose, amino acids, fatty acids. Epinephrine is suppressor for insulin secretion. As I mentioned, insulin is anabolic. I am not going to talk about the mechanism of action of insulin because you already took that in some place. Okay? But this is to remind you about the mechanism of action. I mentioned that it is anabolic, يعني synthesis of glycogen and synthesis of lipids, triglyceride, and synthesis of proteins. Also remember that insulin will increase the glucose uptake in muscle and adipose tissue, but has nothing to do with the glucose uptake in liver and the brain. These are the counter-regulatory hormones of insulin, glucagon and epinephrine. They are doing opposite things. Okay, so insulin, because it is anabolic, so it will decrease all catabolic processes, while the counter-regulatory hormones like glucagon will increase all the metabolic pathways. glucagon is catabolic، حكيت عنها قبل شوي. الآن بدنا نتكلم عن الميتابوليك picture in each of these organs, how each organ will metabolize each of carbohydrates, lipids, and proteins. This summarizes the metabolism of carbohydrates, amino acids, lipids in liver in well-fed state. Okay? Now when you take rich meal, food intake, rich meal of lipids, carbohydrates, and proteins, okay, there will be hyperglycemia, hyperaminoacidemia, and hyperlipemia. And in 0 to 4 hours, and that is called the absorptive phase, okay, everything will return back to normal concentration in the blood. What happened with these? Because of insulin glucagon ratio is high, glucose uptake in the liver will be increased, okay, high concentration, so most of the glucose will enter the liver, and the first thing to be done by the liver under the effect of high insulin to glucagon ratio is the phosphorylation of glucose, and it will be converted to glucose 6-phosphate. Okay, the enzyme that does this process is called glucokinase. Glucokinase, there is another enzyme, another isoenzyme of glucokinase, hexokinase, but hexokinase here is not working. Glucokinase is induced by insulin, and because the glucokinase has higher Km, so it will phosphorylate these high amounts of glucose and convert them to glucose 6-phosphate. That will prevent glucose from returning back from liver to blood. So glucose will be trapped here, and what will happen as glucose 6-phosphate, and because we have plenty of these materials, and because of high insulin to glucagon ratio, this glucose 6-phosphate will be used for glycogen synthesis for storage, because we have excess amount of it, so we store it as glycogen. Some of it will be oxidized, okay, using this pathway. What do we call this pathway? Pentose phosphate pathway. And the reason behind this direction is to produce what? And why we need an ADPH?
To enable it.
Why we need it? Synthesis of lipids. Okay, fatty acid synthesis requires an ADPH. There is another, this is one major source of an ADPH, okay, by going into the pentose pathway. And this is a type of coordination between liver and lipids, okay? Okay, lipid metabolism in the liver. It requires an ADPH, so glucose or carbohydrates will provide this material for protein, for lipid biosynthesis. There's another source of an ADPH, if you remember, okay, malic enzyme will produce also an ADPH. Glucose also will be oxidized to pyruvate. How glucose is oxidized to pyruvate? By glycolysis. So the enzymes of glycolysis، خليني احكي عن الانزيمز هون. ايش هذا الانزيم اللي هون؟ Glycogen synthase, which is activated, okay, or regulated by covalent modifications and by allosteric regulation, okay, covalent modification by dephosphorylation, and when it is dephosphorylated, it will be activated, okay, and it is dephosphorylated under the effect of insulin, okay, not directly but indirectly, because insulin will activate phosphoprotein phosphatase that will dephosphorylate the glycogen phosphorylase and activate it, okay. Here also some enzymes will be activated, okay, because of the insulin glucagon ratio is high, and those enzymes حكينا واحد منهم اللي هو glucokinase، وفي عندنا البيروفيت kinase and PFK1, okay. These enzymes are also regulated by covalent modifications and by some allosteric regulations. So pyruvate will be formed, and this pyruvate will be further oxidized into acetyl-CoA by what? Pyruvate dehydrogenase. Pyruvate dehydrogenase also regulated by covalent phosphorylation, dephosphorylation, by allosteric regulation, and by induction by insulin. So pyruvate will be converted to acetyl-CoA. Now, acetyl-CoA will be used for the synthesis of fatty acids. The enzyme that is responsible for fatty acid synthesis is fatty acid synthase, and one regulatory enzyme, regulatory, but the most regulatory enzyme is acetyl-CoA carboxylase. Okay, it is activated also by dephosphorylation, and it is activated allosterically by citrates. Okay, why it is activated allosterically by citrates? Lambda citrate is carrier of acetyl-CoA. So once it leaves the mitochondria, it will provide more acetyl-CoA. So it will activate acetyl-CoA to be used for fatty acid synthase. Okay? Here, fatty acids will be used for the synthesis of triglyceride. In order to synthesize the triglyceride, you need what? You need glycerol and fatty acids and fatty acid transferases. Okay? Glycerol is provided from glycolysis, which is here, as a glycerol 3-phosphate, and fatty acids will be started to be added on the hydroxyl group of the glycerol to form this lipoprotein, very low density lipoprotein. Okay, so this very low density lipoprotein is rich in triglyceride, and it is rich in cholesterol, synthesized in the liver mainly from carbohydrates. Okay, some from these and some are from these, but much from carbohydrates. So excess carbohydrates, after storing as glycogen, will be converted to lipids, and these lipids are sent to adipose tissue for storage. So as much as you eat carbohydrates, you will form a lot of lipids to be stored in your adipose tissue. Okay? So don't eat much of chocolates or kunafa or these things, because they will be converted to lipids. Some amino acids that come from food, diet, okay, uptake will increase. Some of them will be used for protein synthesis. The synthesis of these proteins represent the synthesis of enzymes in the liver for different metabolic pathways, not for storage purposes. Okay, some of those amino acids will be converted to pyruvate, some of them will be converted to acetyl-CoA, some of them will enter as some intermediates of TCA cycle. We need some TCA cycle energy, okay, for the biosynthesis of these things. Okay, some chylomicron remnants. What are chylomicron remnants? These are the triglycerides that was packaged in the intestine with some other phospholipids and leave the intestine via lymphatic system and enters the circulation, and some of them moves toward liver, okay, and some of them move to the adipose tissue, okay. So the remaining of chylomicrons after they go to adipose tissue. Not all of them will go, some of them. The remnants, or the remaining ones, will come to the liver and provide fatty acids. What is the enzyme here that provide fatty acids from these chylomicrons? Lipoprotein lipase, okay? Because of high insulin to glucagon ratio. I think I covered this. These are the enzymes of glycolysis that are activated by high insulin to glucagon ratio. And these are the enzymes for gluconeogenesis that are inhibited in the well-fed states. And these are the enzymes that are inhibited for glycogenolysis in the well-fed state. You have to remember these enzymes, and you have to know if they are activated or inactivated at what condition, in the fed state or fasted state. I bring some questions about these things. يعني I will bring you, for example, in a well-fed state 10-15 enzyme, okay, and ask you which ones will be activated, which ones will be inhibited. So be familiar with these enzymes, especially the key enzymes. What is the key enzyme in beta oxidation of fatty acids? Did you remember? Carnitine, fatty acid, transferase 1, CAT1 and CAT2. لا لازم يكون.
ما كانوا مطلوبين بس مرة بس ما كانوا مطلوبين.
مش مطلوبين؟ كيف بيدخل الفاتي اسيد للميتوكوندريا عشان يصير له اوكسيديشن؟ كيف؟ يصير له اكتيفيشن، بس كيف بيدخل للميتوكوندريا؟ ايش هي؟ هي الكات 1 كارنيتين شطر. فالكات 1 اللي بيدخل الفاتي اسيد is inhibited by malonyl CoA. malonyl CoA من وين تيجي؟ من الاسيتيل CoA والسي او 2 باي اسيتيل CoA كاربوكسيليز. عشان هيك لما يصير فاتي اسيد سينثيسيس لا يمكن يصير بيتا اوكسيديشن اوف فاتي اسيدز، لانه بكون عندي هاي مالونيل CoA تبعت الفاتي اسيد سينثيسيس، والهاي مالونيل CoA at the same time it will inhibit CAT1. This is what happened in well-fed states in the adipose tissue. Glucose uptake will be increased by GLUT4, which is insulin dependent. High glucose phosphorylation by hexokinase, glycolysis to pyruvate, also an ADPH for lipid synthesis, fatty acid synthesis, hexose monophosphate shunt, pyruvate by pyruvate dehydrogenase to acetyl CoA. Some acetyl CoA will enter the TCA cycle to provide some energy for the synthesis. Okay, so we have high fatty acids from glucose also, as you see here, and fatty acids from chylomicron, fatty acids from VLDL. All of these will be packaged into triglyceride, okay, for storing excess lipids and excess carbohydrates as triglycerides. This is the picture in muscle. The same thing. High uptake of glucose by using GLUT4, which is insulin sensitive. A lot of glucose, okay? Phosphorylation of glucose 6-phosphate. Muscle stores glycogen because it requires for its actions, contractions, and these things. So glycogen will be synthesized. Glycogen synthase will be activated. Some oxidation to pyruvate and acetyl-CoA for some energy, and amino acids used for biosynthesis of some muscle proteins. Okay? This is in the well-fed state. This is the brain. Glucose enters the brain via GLUT1, which is insulin insensitive or independent, glycolysis, pyruvate dehydrogenase, acetyl-CoA, Krebs cycle energy. So brain in the well-fed state depends mainly or depends entirely on glucose. But in a moment you are going to see that brain will change its behavior in the starvation, long-term fasting. It will switch to ketone bodies, as you will see. But still, it requires glucose, but in much less quantity. If it is in the well-fed state, requires 100 grams of glucose for energy production. In the long fast, it requires 30 grams of glucose, for example. It will reduce its dependence on glucose and find another path using ketone bodies. This is a presentation of the well-fed state of different metabolites in different organs. This is what I was talking about in the last half an hour. It is summarized in this picture. إذا نتكلم عن الفاستنج. Fasted state, it will induce secretion of glucagon and low insulin. So we have high glucagon to insulin ratio. So we have catabolic picture. Okay? In the catabolic picture, الميتابوليزم كله بده يختلف in liver, muscle, adipose tissue, and brain. Why? To sustain energy for every cell in the body. So there will be some switches, okay, in metabolic pathways, and the picture that you are going to see is mainly catabolism. يعني راح تشوف glycogenolysis, gluconeogenesis, lipolysis, and proteolysis at different stages of fasting. This represents the glucose and this represents time, and to show you at what time in fasting state what metabolic pathway is active and what metabolic In 0 to 4 hours, we have the ingested glucose. In 0 to 4 hours, it will decrease because the uptake. لأن كنا بالويل فيد state, uptake is high, but glucose enters that, as well as amino acids. And now after glucose is depleted, the ingested glucose, and you continue not taking food, continue fasting, okay, after 3 to 4 hours after the post-absorptive state, okay, glycogen will start to be degraded. High glucagon, low insulin. Activation of a glycogen phosphorylase. So glycogen, okay, will start to be degraded to provide glucose because there is no more glucose. And in 10 hours nearly, it will be done. Very little of a glycogen will remain. In 10 hours from the last meal. Okay? At the same time, there is a gradual increase in gluconeogenesis. And the most active time for gluconeogenesis in the first 3 days of fasting. يعني أول شيء بيبدأ في glycogenolysis, ينتهي glycogenolysis. At the same time there is a gradual increase, okay, ولكن في الأول يعني اليوم الثاني والثالث okay بيكون في عندنا الجلوكونيوجينيسيس. Then glucogenesis rate will decrease, as you see, and this is very important. Because if you continue, if the body continues doing the gluconeogenesis, what will happen? What are the substrates for gluconeogenesis? Amino acids. Mainly amino acids. Okay? Some glycerol, some lactate, but mainly amino acids. Amino acids are coming from your body protein, muscles. So, if gluconeogenesis continue, your protein, your muscle proteins will be degraded, and that is incompatible with life. So, gluconeogenesis decrease rate, and at the same time, fatty acids تصير lipolysis من الاديبوز tissue، والfatty acids تطلع هي والجليسرول، والfatty acids تروح على الليفر and other tissues، ويبدأ يصير لها بيتا اوكسيديشن، تروح على المصل وتروح على الليفر، يصير بيتا اوكسيديشن. Liver at that time, because there is no more food and the brain requires some other source of energy, there is not enough glucose by the long term of fasting or starvation, liver will start making ketone bodies. Okay? And synthesizing them and sending them to brain. لأن البرين تقريبا 30% of its energy only from glucose, from gluconeogenesis, and more than 55 to 60% will get it from ketone bodies. So ketone bodies, especially beta hydroxy butyrate. Beta hydroxy butyrate will provide about 50% of brain energy from beta hydroxy butyrate, 30% from glucose, 5% from acetoacetate, and 15% from amino acids.
لما الجلوكونيوجينيسيس هذا الديكلاين كمان ممكن نحكي السبب انه مثلا الاوكسالو اسيتيت بيقل المفروض لو استهلاك جزء منه.
طبعا هذا جزء من الريجوليشن. يس. This is what happened in liver under fasting conditions. When the glucose level in the blood? When the amino acids? When the lipids? Where no? No, they are not there because there is no intake of any food, no food intake. وبالتالي now the liver will behave differently from the fasting, from the well-fed. Well-fed state كان الجلوكوز يدخل والامينو اسيدز تدخل والفاتي اسيدز. اوكي؟ بينما هون opposite. Store the glycogen because we need glucose. And this is the importance of storing excess food because they are required when necessary. This is one of the strategy of metabolism. Glycogen. By glycogen phosphorylase will be converted to glucose 6-phosphate. And why glycogen phosphorylase is activated? High glucagon to insulin. G protein, adenylyl cyclase, cyclic AMP, protein kinase A, phosphorylation of glycogen phosphorylase activation. So it will degrade the glycogen to glucose 6-phosphate. Fortunately, liver has an enzyme of glucose 6-phosphatase. Other tissues do not have glucose 6-phosphate. Muscle does not have it. So glucose 6-phosphate will be converted to glucose. Glucose will leave the liver to peripheral tissues, to brain, to red blood cells, because they are obligatory on glucose as a source of energy. Okay. At the same time, في fasting, late fasting بيصير lipolysis لأنه catabolism لأنه high glucagon. Adipose tissue, triglyceride stored here will be degraded into fatty acids and glycerol. What is the enzyme that degrades these triglyceride in adipose tissue? Hormone sensitive lipase activated by high glucagon بصير له phosphorylation بصير له activation. هذا الهرمون sensitive lipase يختلف عن اللايبو protein lipases. Okay? Fatty acids and glycerol, fatty acids enter the liver, beta oxidation to acetyl-CoA. Now, this acetyl-CoA is used for the synthesis of ketone bodies. A lot of fatty acids oxidized ketone bodies, especially at the late fasting, prolonged fasting, and these ketone bodies will be gone to brain. Okay. Now what will happen to this glycerol that coming from the stored triglyceride? It will be used for gluconeogenesis. Okay? It will be used for gluconeogenesis because the liver has the glycerol kinase and it will enter the gluconeogenic pathway. Okay? Some amino acids also will provide some acetyl-CoA. Some of them will be converted to pyruvate. Now, we don't have, like in the well-fed state, activity of pyruvate dehydrogenase. Okay? Mainly pyruvate is used for glucose synthesis, not to be converted to acetyl-CoA, because we have a lot of acetyl-CoA from here. Okay? This is an adipocyte, adipose tissue. Stored triglyceride will be hydrolyzed by hormone-sensitive lipase into glycerol and fatty acids. Glycerol will leave. This is the coordination. This is the transfer of substances from one organ to another organ when it is needed. So glycerol will go to the liver, fatty acid to the liver for beta oxidation, acetyl-CoA making ketone bodies. Okay? Some of these fatty acids will be oxidized comparable to this in order to enter TCA cycle to have some energy. Okay. Is there any gluconeogenesis in adipose tissue in the fasting state? No. Okay. Depends on the acid. This is in the muscle. In the muscle, fatty acids coming from adipose tissue, ketone bodies from the liver, beta oxidation of fatty acids to acetyl-CoA. Acetyl-CoA is enter TCA cycle for some energy. Proteins are degraded into amino acids. These amino acids leave the muscle to liver for gluconeogenesis, for brain and other tissues. Okay? Is there any glycolysis here? No glycolysis. It depends on the acetyl-CoA that comes from fatty acids. Is there any gluconeogenesis in the muscle? No. Muscle is not gluconeogenic organ. Liver is and kidney are gluconeogenic ones. This is a comparison between fasting and long, prolonged fasting or starvation. The same thing happened nearly, except some using of ketone bodies that are synthesized in the liver. Instead of sending to the muscle, they are completely sent to the brain. Okay, with also some differences of some amino acids and during formation. تقريبا حكينا ايش اللي بنستخدمه في الهرمون. 30% of energy requirement of the brain is met by glucose in prolonged starvation. 50% by hydroxybutyrate, 5% by acetoacetate, or 15% by amino acids. Prolonged starvation ends with death or refeeding. And not more 3 weeks, okay, of starvation one could survive. Obese people could survive more. Why? Because they have lipids, a lot of lipids stored. فبضلهم يعتمدوا على البيتا اوكسيديشن والفاتي اسيدز والكيتون بوديز. This is in the prolonged fasting or starvation. Drain depends on ketone, that is. Okay? And mainly beta hydroxybutyrate. Some glucose coming from gluconeogenesis. TCA cycle to oxidize the acetyl CoA that comes from here or that comes from here. In the late fasting, okay, kidney will participate in the process of gluconeogenesis. It will provide glucose for also other tissues using some amino acids as gluconeogenic substances. This material is coming from Living Pot, second edition, chapters 23. Okay? We are done with integrated metabolism, well-fed state, and fast. Now, what remains is the obesity, diabetes, and obesity. I suggested that I record this lecture and send it to you because there are no students attending lectures nowadays. Is that good with you?
Yes, sir. Preferable.
Preferable. So today, this night, I will record it and upload it on Teams. Okay?
Yes. Appreciated, doctor. Thank you.
Okay. Spare some time for you to study.